So we've just gone through the sort of exercise mathematically of figuring out both mathematical expressions for what the forces are acting in this pogo stick, so there's a gravitational force and a spring force, and also of thinking about how to express the momentum in this coordinate system that we've chosen. So we've got a coordinate system where the pogo stick has some length d that can change in time. The pogo stick is oriented with an angle theta with respect to the ground, and the center of mass of the person is located at some distance L away from the pogo stick, normal to the pogo stick. So using that coordinate system, you'll recall that we figured out an expression for the position of the person. So the position vector x defines the person's position, for the velocity of the person, for the momentum of the person, and finally for what the time rate of change of that momentum is. And of course, that now allows us to say that the time rate of change of the momentum, which has all this stuff in it, must be equal to the sum of forces acting on the object. And so here we've got the sum of forces acting on the object, gravitational force and the spring force. And of course up here there are a bunch of different terms having to do with radial acceleration along the d-hat direction, having to do with Coriolis type acceleration, centripetal acceleration both in the d-hat direction and the theta-hat direction because of the fact that the person is offset both in the d-hat and in the theta-hat direction, and so on. Now the final thing that we did, of course, is to take these expressions for the forces, and translate them into a consistent coordinate system with the left-hand side where we've got normal unit vectors so that d-hat and theta-hat are orthogonal to each other, which allows us to say that all the d-hat stuff on the left-hand side must be equal to the d-hat stuff on the right-hand side. So that's what we did. And what I want to do now is collect some of those terms and skip over a little bit of the algebra and spend a little bit of time just thinking about whether this actually makes sense. So I've done a little bit of cleanup of this, and not very much cleanup. All I've done is I've collected the theta-hat terms from the left and the theta-hat terms from the right, and the d-hat terms from the left and the d-hat terms from the right, so you can still see things that look pretty familiar here. For example, this is just the spring force divided by mass. This is the component of the gravitational force that's along the d-hat direction, and so forth. And the question that you should be asking yourself at this point when you get to this, whenever you're dealing with a system that's complex like this, or where the equations are complex, is how do I actually know if these equations work? I mean, they look nice and everything, but what are some ways to actually assess whether they make sense? And the best advice, or one good piece of advice I can give you, is think about what are the limiting cases here. Do these equations of motion reduce to equations of motion that make sense in some of the limiting cases? And I'll propose a couple that we can think of. I'll propose the easiest one first. Case one is the case where we take the simple case of the complicated case of the pogo stick, and we say, how could we reduce that to something simpler? Well, one thing we could do is we could simply turn off gravity, and we could also make this length go to 0. So let's turn off gravity and make the length go to 0, at which point you have a fairly simple situation of a mass on the end of a spring with no gravity present. Now, when you do that, pretty clearly a lot of things are going to go away. So length is going to 0 and g is going to 0 here. So for this limiting case, these terms will go away. For this limiting case, you can also see that L is 0, so this term goes away and this term goes away. And once I've made those things go to 0, I can also see that I've now got d double dot is equal to, well, let's think about what d double dot is going to be equal to. I can collect terms. I can bring this over this hand side. This is 0, this is 0, and so I get k over m times d naught minus d plus plus d times theta dot squared. So what does this actually mean? Does that make any sense? This says that the length of the spring in time, that the distance of the person from the center, the acceleration of that person in the radial direction, is going to have two components. One component is due to the spring, which makes sense, right? If you compress the spring, they'll get pushed out. If you stretch the spring, they'll get pulled in. And the other component is what looks like a centripetal acceleration component. When the system is rotating around the origin, there's going to be an additional acceleration outwards due to the rate of change of theta. So that's the one case that makes reasonable sense. A second limiting case that we could think about is what if instead of thinking about a spring, we keep gravity on, but we go from this to this. So in other words, we make that spring be a constant length. So we make d constant and L go to 0, right? So it's still going to be located at some angle above horizontal. There's still going to be gravity present. But when I make d constant, what that does is it says the spring can't change length. That means that d double dot must be 0, and it means that d dot must be 0. Well, if that's the case, then this first equation becomes pretty simple, right? If L is 0 and d dot is 0, the first equation turns into theta double dot is equal to minus g over d times cosine of theta. And let's think about whether that equation is one that makes sense. Well, when theta is 0, this is basically a pendulum that's horizontal, and if I were to let it go, theta would drop down and would become more negative, right? Well, when theta is 0, cosine of theta is positive 1, so the angular acceleration is minus g over d. That makes sense. When theta is pi over 2, right, the pendulum is vertical. There is it's going to be at an unstable equilibrium at this point. So when theta is pi over 2, I would expect theta double dot to be 0. Cosine of pi over 2 is indeed 0, so theta double dot will be 0 when the pendulum is vertical. So this is another limiting case that actually makes reasonable sense. A third limiting case that would be good to do, and I'll maybe transition to a separate. So case 3, what happens if we require that d be 0? So we're actually going to, and L not be 0. Okay, so what this case is actually saying is that we go from this to a case where we basically take this point and move it down to the origin. So we're actually looking at a situation like this, where still theta is defined in this way, but now there's not going to be any motion along this. This point is going to be fixed. Well, if we look at that case, d is 0, L is non-zero. Since d is 0, that also implies that d dot must be 0. So and d double dot must be 0. So let's look at the second equation to get some sense of that. D double dot is 0, d is 0. The second, and on the right-hand side, the only way d can be 0 is also if d naught is 0. Otherwise, we'd actually have an acceleration in the d hat direction. So the only way that this is going to work out is if we actually have theta double dot is equal to g over L sine of theta. Well, let's think about whether that makes sense. What happens when theta is 0, first of all? Well, when theta is 0, the object is actually located up here, right? So when theta is 0, theta double dot actually should be 0. It should be balanced, right? So that makes sense. And you need to think about that for a second. Theta being 0 actually means that since this is the person's arm, the pendulum is vertical, right? On the other hand, if theta is pi over 2, right, when theta is pi over 2, then the person is actually located here, right? This is when theta is pi over 2. And the person will be located here. And in that case, the angle is going to tend to increase in time. Well, sine of pi over 2 is positive. Theta double dot is g over L times 1. I'm going to get a positive increase in theta, so that's another case that makes sense. So at this point, we've run through a number of cases, a case that involves the spring force, a case that involves the offset in the theta hat direction, and a case that involves the offset in the d hat direction. And in all three cases, we get equations of motion that make sense. Now, that doesn't mean that this is right. In fact, I have not checked 100% to make sure that these equations of motion are right. But certainly at this point, I've got some reasonable confidence that they're right because I've run through 3 different limiting cases and have gotten equations that actually are sensible for those limiting cases.